Observe the motion of these particles carefully. Chaotic noise coalesces, remelts, and crystallizes into a structured grid. Standard sequential generation relies on left-to-right prediction. The model locks in one word at a time, moving forward without the ability to structurally reconsider what it just wrote. Masked diffusion models attempt to solve this by using static sentinel tokens, but they still rely on a one-way commitment. Once a position is unmasked, the token is fixed. DiffusionGemma departs from these methods by using uniform state discrete diffusion. The generative process begins in a state of maximum entropy. The scheduler draws every position uniformly from the entire 262,144 token vocabulary. This high-entropy state renders as a polyglot cascade, a flicker of katakana, Bengali, and CJK characters that indicates the model has not yet narrowed its focus. Capturing this transition in real time is difficult because probing the model's internal state often collapses the very dynamics researchers want to observe. The 0.3.0 release of the DiffusionGemma node pack for ComfyUI solves this observation gap. This version functions as a deterministic lab bench built to expose the internal mechanics of the model at every step of the run. Identifying how these models reason requires a way to manipulate the face transition during decoding to watch the language settle into its final form. Text generation in this context is better understood through the lens of statistical mechanics rather than simple image denoising. We can view the process as simulated annealing. This is the melt state. It is a flat distribution across the vocabulary, where each position holds exactly 18 bits of entropy. The temperature schedule initiates a cooling process. Dividing the logits by a shrinking temperature sharpens the distribution, forcing the entropy of individual positions to fall as the run proceeds. Freezing is governed by the EB sampler, or entropy-bound unmasking rule. The model accepts only the lowest entropy prefix of positions that stay within a specific cumulative error budget. Any position that fails to meet this entropy bound is rejected by the scheduler. These unaccepted positions are thermally agitated, returning to the 18-bit melt each step to be redrawn. This renoising process provides the model with a native form of self-correction. There is a common critique that diffusion models cannot edit their own mistakes during a generation. In this uniform state model, a token can commit to the canvas, but if its entropy rises as the context shifts, it can remelt and be replaced before the sequence reaches its final state, meaning crystallizes out of noise. This gives the model a capacity for dynamic revision that masked diffusion lacks. This nodal flowchart shows how those mechanics are mapped onto a ComfyUI network. The 0.3.0 architecture is organized around a series of exposed generative seams. Measuring these phase transitions accurately depends on absolute seed determinism. The 0.3.0 release implements a stability fix that tears down forward hooks strictly after every run. Isolating the run state in this way prevents cross-contamination and ensures that identical settings produce identical results every time. For the first time, the DGemma trace summary node provides a direct readout of the crystallization process. This version corrects the reporting of the committed fraction variable. By treating this fraction as strictly block local, the tool avoids reporting false remelts when the generation crosses from one block of text to the next. The engine now captures telemetry directly from the generation loop. This includes Tier 0 predictive entropy. It also captures pre-excision token IDs before the model finalizes its decisions. These specific internal variables provide a repeatable framework for measuring and verifying how the model arrives at a specific answer. With the 0.3.0 baseline stabilized, work can begin on the exploration targets documented in the roadmap. Currently, tokens jump directly from high-entropy noise to a frozen state. The next major research goal is liquid state decoding. This would represent a state where a token is dynamically mobile, but remains structurally coherent, a liquid phase between the melt and the solid. This scatterplot helps map these behaviors across multiple dimensions. By charting the cooling protocol against the entropy threshold, we can identify the boundaries where a claim stays stable or where it flips. The third axis in this map is the renoise axis. Standard uniform state diffusion draws rejected tokens from purely random noise. The core hypothesis involves swapping that random noise for a distribution biased toward plausible alternatives. Under this swap, the intermediate melt would no longer be a polyglot soup, but a cloud of near meanings. The native socket types established in the development records make these experiments possible on the Comfy UI bench. The 0.3.0 release gives researchers the tools to map the liquid state decoding boundary and measure how language models reason through the noise.